All right, I'm going to go ahead and introduce our next speaker, who is Dr. Celso Castro Bolinaga, who is an associate professor in the Department of Biological and Agricultural Engineering at North Carolina State University. He graduated from Universidad Católica Andrés Bello in Venezuela with a BS in civil engineering and received an MS and PhD in civil engineering from Virginia Tech. His team, the Environmental Sediment Mechanics Research Group, conducts studies in the area of environmental hydraulics and sediment transport, studying phenomena related to the dynamics of water and sediment in a range of aquatic environments that include streams, rivers, and estuaries. His research portfolio has been sponsored by the NC Department of Environmental Quality, NC Department of Transportation, and NC Water Resources Research Institute, USGS, USDA, NOAA, and NSF. So go ahead whenever you're ready.
All right. Thank you, Carolina, for the introduction, and thank you for the invitation. I'm really excited to talk about a topic that let me just make sure the usual Zoom presentation. Can you see my screen and the pointer?
Yes.
Yes, okay. So I'm really excited to talk about a topic that we started working on as soon as I arrived to NC State. And it's not only has been with us for some time, but also our thought process have evolved as we have collected more and more data across the state of North Carolina. The title of the presentation is a bit different to what is on the agenda. So today I'll be talking more about characterizing variability to advance predictability of stream bank erodibility parameters. So the title that refers to the probabilistic erosion curves, that's something that we're working on, and I'll touch base on that towards the end of the presentation. Before I start, I would like to acknowledge my students from my research group. So Alexis Swanson, which is a former PhD student, and then Carol Sanchez and Sam Holberg, which are both PhD students currently in the group, as well as collaborators that have contributed to this project, Chrissy Hopkins from USGS, and then Perry R. Russell from NCDEQ. And the work that you're going to see today is actually coming from two different projects. One that was funded from DEQ in 2018, that's already done. And then one that we're currently working on that is funded by WRRI. So there will be hopefully many more things to come after we're done with this project. All right, so I would like to start by sharing basically the part of the letter that was published when the Nobel Prize in Physics in 2021 was awarded. And the reason why I start with this is because I think it really captures what we're trying to do with the stream bank erosion, especially these last three sentences. So basically what it says is that without understanding the origins of variability, we cannot understand the behavior of the system. And I think this is something that is guiding our thought process, not only in the projects that are related to stream bank erosion, but also in the other projects that are related to sediment transport that we're working in our group, such as dam removal, bridge scour, stream restoration, among others. In general, what is driving the variability of the processes that we're seeing in streams and rivers is climate change and the impact that climate change is having in the volume and timing of water delivery to rivers. So if you see these two pictures, they are from a paper that was published in 2022 by Sibitsky. This is one of those seminal papers that basically try to look at sediment budgets at a global scale, so very large quantities and very large spatial scales. So what you see on the picture on the left is basically Anthropocene sediment loads in gigatons per year. And you see the ones from 1950 in blue to your left, and then the ones in 2010 in green to your right. And of interest here are, for example, the amount of sediment that has been deposited in reservoirs. So you can see that it has gone from 2.8 gigatons per year to almost 65. And also the amount of soil erosion that has been accelerated because of the impact of human action. So all of this primarily is not only affecting the input that we are receiving in streams, but also in some cases, the amount of sediment that streams are transporting over time. And then what you see on the right is basically a prediction of how the sediment load in rivers will increase depending on the average basin temperature and then the degrees of warming. And you can see that depending on the temperature, 1 or 2 degrees can actually increase by an order of magnitude what will be the sediment load that is going to enter in our streams, in addition to the changes in the timing and the volume of water. So the topic that we are covering today, stream bank erosion, it's can be severely impacted by these changes, right? This is a natural process that takes place in every stream. The problem is that when pronounced, then it can really impact the stability and the functions of the stream. So it can change the platform by creating erosion or deposition. It can affect infrastructure that is close to our streams. And it can also impact water quality, not only locally, but also in the downstream reservoirs that are capturing and receiving all of this sediment. The example that you see here in the screen is from our very first site that we started doing measurements in Richland Creek in the city of Wake Forest, a bit north of Raleigh. And this is a stream that was restored in 2010. And then after that, it has undergone a significant amount of bank erosion, and with that, erosion and deposition along the ridge. So the three cross sections that you see on the top right corner of the stream are in yellow is the design geometry for this particular cross section that you see on the screen. And then the ones in red are in blue are the cross sections that we measure after the red one, after 8 years of restoration. And then the blue one, just in a period of 4 months after we measure the red, because and the changes were generated because of two events, basically Hurricanes Florence and Hurricane Michael, or the floods that were originated from those hurricanes. So you can see that bank erosion, yes, it is a problem locally because it will change the stream, but it will also change the capacity of the stream to effectively and efficiently convey water and sediment downstream. So in particular, today I'm going to focus on stream bank erodibility parameters. And the reason why I'm focusing on this is because these two variables are fundamental to advancing our prediction capacity for stream bank erosion rate. So they are the foundation of us getting to a better place in terms of accurate predictions. So the stream bank erodibility parameters, I'm specifically be talking about two variables. One is the critical shear stress, which is the force, the minimum, or the maximum force that you can apply to the sediment before the sediment starts moving. So it's basically related to the onset of erosion. And then the coefficient of erodibility, it just has to do with how fast the sediment will move after erosion is taking place. So one will give you an idea of the threshold force that you need, and the other one will give you an idea of how fast the sediment will detach after sediment is moving. And what you see on the screen right now, it's beyond the details. This is just meant to provide an example of existing relationships for the critical shear stress. And what I want you to focus is on all of the variables that are listed at the bottom. So this is a topic that has been around for some time. And there has been many efforts to try to develop relationships that actually capture or are useful to predict that threshold force for erosion. Less study has been focused on the coefficient of erodibility, which we typically assume is inversely related through a power law function to the critical shear stress, as you see on the screen. And what it ended up happening is that we collected a lot of data for tau C and tau sub C, tau C and K sub D, and basically we correlate these two variables. And then we ended up with equations that are basically similar to the ones that you see in the screen right now. And these equations are dependent upon a good characterization of tau sub C. So if uncertainty is basically affecting that equation, then that will be immediately propagated through the coefficient of erodibility. And the challenge is that for many materials, sandy soils or streams that has a high percentage of sand, the critical shear stress will not be as relevant as erodibility coefficient. So we expect that material to move. And for us, it's more of a dynamic process, and that we are interested in understanding how fast it will move once it starts. So the way these parameters go into the model of stream bank erosion is through the equation that you see on the top. And this is the only equation that I have in my presentation. This basically predicts the erosion rate as a function of the excess shear. So basically the difference between the amount of force that the water is applying and the critical force that is related to the sediment. And then based on this excess shear and an exponent that is equal to 1, the erosion rate is basically calculated by multiplying that through times the erodibility coefficient. So this equation is embedded into mainstream models. So it is embedded in the USDA bank stability and tow erosion model to calculate erosion. And at the same time, it is embedded in the one-dimensional version of HEC-RAS that has BSTEM included in it. So it's actually an equation that it becomes the center of what we do right now for predicting how much stream bank erosion will occur if we're using process-based modeling for this. So the question that we were trying to pursue with these two projects is basically how do stream bank erodibility parameters vary in response to rapidly changing hydroenvironmental conditions? And by hydroenvironmental conditions, I'm going to specifically be talking about changes in discharge, about changes in moisture content, changes in temperature, and changes in electrical conductivity along the bank face. So if you see this picture that I have in the screen right now, this is an unnamed tributary to West Fork in Kernersville, North Carolina. What I like about this picture is that you can really see a bank that is free of vegetation along the face, and you can see the different materials and basically the layers of the different materials. And you will see why these questions came to be in a few minutes. But what we're trying to understand is how, if you have a different flow regime, if you have a different variability of discharge in these streams, how are those compounding effects between that variability and the material actually going to affect erodibility parameters? So can we consider this to be just a function of soil like we do right now? It's based on the material, more for clayey soils and less for sandy soils. We're talking about critical shear stress, or is this something dynamic that will actually change daily or seasonally? So for this, again, I'm going to show you results from two different studies. We're trying to characterize variability through the lens of first streams across the North Carolina Piedmont region. And this is the part of the study that was funded by DEQ in 2018. And then the ongoing work, which is basically focusing on streams within the city of Raleigh. And the main difference between these two is that in the one to the left, so the DEQ funded study, we were looking at spatial variability. And the whole study was driven by the idea that soil properties control erodibility parameters. Therefore, we should be sampling as many streams as we can across a big spatial extent so that we capture that soil variability, and therefore we can have equations that can predict erodibility parameters more accurately. What you will see is that soil properties is still part of the story, and temporal variability is also important. And that's the origin of the project that was funded with WRI, and it's the project that we're working on right now. All right. So for the study area, in the regional study, we focus on streams located across the North Carolina Piedmont region. But as you can see in the map, we really had a critical mass of streams that were in the city, across the city of Durham. And the reason for this is that because they had about 5 to 6 years of stream bank erosion profiles that we could actually use also to verify the results that we were getting from stream bank erodibility parameters. So we try to maximize not only the collaboration with them and the EQ, but also the amount of data that was previously collected in these stream banks, including also the presence of USES gauge. But in total, we did 12 different streams, 25 banks distributed along those 12 streams. We have watersheds that range from relatively small to 21.8 square miles, and then streams that were highly rural to streams that were more urban, especially those around the city of Raleigh. And again, these streams were mostly around the Raleigh-Durham area just because of the collaboration with the city of Durham. So the field measurements, they were primarily based on 3 different components. So we collected soil cores for soil physical characterization. We measure moisture content, electrical conductivity, and soil temperature using a soil probe. And then we perform in situ jet erosion tests for estimating erodibility parameters, the one that I mentioned before, the critical shear stress of tau sub C, and then the erodibility coefficient K sub D. So when you see on the screen going from left to right, here you can see the Hydragov profile. That is the sensor that we use to measure the instantaneous values of these 3 hydroenvironmental conditions. Then the soil cores that we collected to actually characterize grain size distribution, bulk density, Atterberg limits, and coefficients of uniformity and curvature of that material. And then what you see on the right is a device that we have in our group that basically allows to measure erodibility parameters in situ, so the jet erosion test. And I will provide more details about how the jet works in the next slide. But what you can see here is that the device is basically generating a scour hole in the bank. and that scour hole is driven by a head tank, which basically sets the force that we are applying into the bank. So the water goes from the head tank to the jet, and then on the picture farthest to your right, you can see the jet erosion test actually deployed in the bank. And then this basically is the device that will release the jet of water, and then we will measure progressively the development of the scour hole. So for that, if you focus your attention on the right part of the screen, you will see basically a drawing of the jet erosion test. So as I said, this is basically a jet of water that will progressively scour the bed. And then after a certain amount of time, we deploy a point gauge. And through that point gauge, we measure the distance that jet eroded the bed over a particular time interval. And then after that, you can see a scour hole, how it looks after a test. The shape of that scour hole is highly dependent on the material. So this material that you see is material that is finer, so high percentage of fines, silt, and clay. And then for that, you have holes that are relatively deep and that are narrow. In sands, you will see more holes that are larger in diameter, and then they will not be as deep as the ones that you see right here. But as I said, the way we run the procedure is basically we release the jet of water. And then what we do is that we start with relatively small time intervals. So we typically start with 15 seconds. And then we run the jet repeatedly until we get 3 consecutive measurements that do not change. And after that, we increase the time interval to 30 seconds, 1 minute, 2 minutes, and 5 minutes. So basically what we're doing is that because we know the force that is being exerted by the head tank, we know the applied force that we are exerting in the bank. And by changing the time interval and measuring the depth of the scour hole, we are basically generating an erosion rate. So at the end, we have basically a set of erosion rates that were developed over a range of applied shear stresses. And from that data, then we can get the erodibility parameters, as I will show you in this slide. So these are 2 representative examples of jet erosion tests that we perform across the North Carolina Piedmont region. And the idea that I selected these 2 is because these 2 show different behaviors, right? We have one on the left that basically have a relatively low applied critical shear stress of 1.6 Pascal. And then you have a form of the erosion behavior that basically the rate of increase of the erosion rate decreases as the applied force increases. So you will see that in the exponent alpha basically being less than 1. And what you see on the right is a soil which the applied critical shear stress is much higher. It's around 13 Pascal. So you require a larger force to actually initiate erosion. But then you can see that the behavior is different, right? It's the opposite. You have an alpha that is an exponent that is more than 1, meaning that the rate of erosion rate increases as you increase the applied force. And as I mentioned, the idea of characterizing this behavior beyond how much force you need is that during high events, these critical shear stresses will typically be overcome, right? So you are going to be looking more at how fast this sediment is moving and detaching, than rather whether this sediment will move in the first place. All right, so this is just a summary of the field measurements. And the idea here is that I just wanted to show the range and the variability of all of the different banks that we measure across the Piedmont region, and also the variability in moisture content, electrical conductivity, and soil temperature that we characterize. You can see here that we measure banks that were relatively highly erodible from 1.2 all the way till 40 Pascal, which is less erodible. And then we characterize material that was primarily sand, as you can see in the soil texture. I think one of the reasons why we targeted banks with high percentage of sands is because the places that we selected were experiencing erosion. And that makes sense that this material was going to be coarser and was going to be more erodible. So that's one of the things that we address for the second part. But in general, we try to characterize a broad range of conditions that allow us to somehow make sense of the data and be able to arrive to a statistical model, a predictive equation to predict critical shear stress and erodibility coefficient. All right, so I'm going to show you 2 sets of results. They look fairly similar with the difference. At first, we're going to look at the critical shear stress, and then we're going to look at the erodibility coefficient. So let's start what with what you are seeing on the top right corner. This is basically a correlation matrix of the critical shear stress, the erodibility coefficient, and alpha, as you can see in my pointer, correlated with all of the variables that we determine either from the soil prof or from the soil course. So you can see here moisture content, temperature, electrical conductivity, the median grain size, the percentage of clay and silt, the coefficient of uniformity, of curvature, and then the geometric standard deviation. So these three are just a function of what is the range of sizes that you have in your sample. So it can still be characterized by the same median size, but then you may have a broader or a narrower distribution of grain sizes along that sample. And then what you see on the bottom, these two main graphs are basically showing the critical shear stress on the y-axis. So basically the force that you require for the initiation of motion. And then you're seeing the moisture content on the x-axis in the plot to the left, and then the coefficient of uniformity on the x-axis on the plot to your right. So the coefficient of uniformity specifically will target that range. So higher coefficients of uniformity, around 40, will mean that you have a large range of grain sizes in that soil, whereas you tend towards 0, you will have material that is more uniform. So it will be from less uniform high values to more uniform lower values. And the reason why we selected these two is because they show up in the correlation matrix as variables that are important in general for both tau sub c and k sub d. So in terms of results, what we saw is that the critical force that you need to initiate erosion generally increase with increasing moisture content and coefficient of uniformity. So if we think first about the coefficient of uniformity, that's a bit easier to understand, because what basically means is that the larger the range sizes that you have, so if you have finer particles combined with large particles, then you will require a larger force to actually initiate that material. So if you have coarser material, coarser sand, then that will require more force to actually initiate that. And then with the moisture content, what we saw is that the general trend, if you account for all of the data, they indicate that they are positively correlated. But if you take a look really at more specific soil conditions, then you see that the story is not quite linear. If you see this, the plot for moisture content and critical shear stress, I have highlighted two types of soils. So the ones with the red circle around it, these are soils that have less than 10% of fines. So these are primarily sandy soils, where only less than 10% of the material is clayed and silt. So the very, very fine portion of the soil. And then the circles that are basically surrounded by a black circle, these are where the percentage of fine is more than 50%. So this will be soils that are very fine, where more than 50% of the material is composed of clay and silt. And what you see is that for the soils that are coarser, you actually have a much better correlation where moisture content, where critical shear stress is increasing with an increasing moisture content. So think about a sand that a sand or a more coarser soil, and when it becomes wetter and wetter and wetter, then you basically require more force to entrain that material. But again, these are soils that are on the very lower limit of the percentage of fines that we characterize. And then if you think about the soils that have more than 50%, what you see is actually the opposite, right? You see that the brightest yellow indicating basically the larger percentage of fines will have a lower value of the critical shear stress. And then you have actually an opposite trend where the higher the percentage of fine, then you start reducing that critical shear stress with the moisture content. So what I'm trying to convey is that because we went to every site and because we collected this only once, so basically the moisture content is just a coincidence of the time that we were able to go out and to measure. We really have data sets that are representative of one instance in time, rather than just like the actual spatial variability. So it's more, there is much more nuance to this than what we actually captured just with this study. And you will see that in the next few slides. And then with the erodibility coefficient, we actually found the opposite trend. So it's weekly, so the erodibility coefficient weekly decrease with increasing moisture content and coefficient of uniformity. So it's actually the opposite trend of what we saw with tau sub c. which is actually well established. But again, if you separate the percentage of fines less than 10% and more than 50%, what you see is that the story, again, is not quite consistent. So you see that this decrease is much more marked for material that is coarser. And then when you see the material in the black circles that is actually very, very fine, you see that the trend is not actually quite as strong. And what we saw when you add actually this same type of variation for the coefficient, what we saw is that the soil properties are actually very effective in modulating the critical force, but then the hydroenvironmental conditions actually are much more effective in modulating the behavior of that material after it starts moving. And that's basically the main conclusion that we arrive in this stream, in this regional study. So the soil properties appear to modulate that initial force. So whether I have a clayey sand, whether I have a more clean sand, or whether I have gravel, that will be important in modulating that force that I need to initiate the erosion process. But then depending on how wet the soil is, how hot the soil is, or the electrical conductivity, which accounts for the relationship between the two, then that will depend the functional behavior. So I can have the same bank made of the same material, but then if I'm looking at an event that happened after 2 weeks of no rain, that bank I expect to behave differently than if I'm having the same event, but then the bank is very wet because I have a significant amount of rains in the day before. The challenge is that we saw a lot of points in the middle that were very difficult to explain statistically. And that basically led us to the second study. So now that we have an understanding of the spatial variability as impacted by conditions that can change daily or seasonally, then the second study basically focused on that temporal variability. So we basically focus on going repeatedly to the same stream and do the same type of measurements, and then try to understand how exactly the same soil changes its behavior over time. For this, we selected streams that were close to campus. So we selected 2 sites in Castro Creek. So Castro Creek site 1 is the one you see on the top left. Castro Creek site 2 is the one you see in the middle. And then Walnut Creek site 1 is the one you see on the right. So Castro Creek, the site number 1, that's actually selected right downstream of Onset Park. So it's a stream that actually going to that field site is quite nice. It's a beautiful place, forested watershed, and you can see that the banks are actually covered with vegetation, and the conditions is not as flashy as you will see on the other 2 sites. Castro Creek site 2 is actually downstream of that. It's in an urban area, and you will see that the stream, if you walk along the stream, you will see much more bank erosion and changes in erosion and deposition levels across the stream. And then Walnut Creek, this is actually the closest place to campus. This is a site that has experienced significant change since we started the measurements. And it is very flashy naturally, and also it is downstream of Lake Johnson, meaning that when we have severe events, they will release water from Lake Johnson, and these banks will actually be submerged for longer periods of time that they will be naturally. So that also gave us an opportunity to collaborate with the city on Raleigh and actually inform them whether what they were doing is helping or not to mitigate stream bank erosion. In the table, you can see some of the characteristics for these watersheds. But again, what we were trying to look is for variability in materials, which you will see in the next slide, variability in the discharge, both the mean daily and also what is the maximum event that they have experienced. The last thing that I want to mention about the study sites is that we try to select points that were capturing either the variability along the toe, as you can see, for example, in Castro Creek site 1, points A and B, or you can see also in Castro Creek site 2, A and B. So these are points that are closer to the toe. They are separated by a certain distance. And for example, in the case of Castro Creek site 2, the location B that we selected is actually downstream of this tree that has been falling for some time. And then that tree is actually acting to block the amount of moisture content that you'll get, or the amount of water that bank is exposed to. And then we were expecting to see more variability, even if the sites are selected in the same stream. And then in Walnut Creek, we have, and this is the one that I'm gonna focus more on the results. because we have one point that is actually close to the upper part of the bank, one point that is close to the toe on the same side, and then we have another point that is located on the opposite bank's toe, that the material is actually quite different, and you will see that in the characterization. So the methodology was the same that we applied for the regional scale study. Here I'm showing the two students that are actually leading this work and going about every 10 days to collect the measurements. So on the left, you have Sam Holberg collecting a soil core at Countryside 2. And then on the right, you have Carol Sanchez actually running a jet test in Countryside 1, downstream of Olmsted Park. So they go to every site about every 10 days, depending on the weather. And then we have marked the sites where we'll do the jet testing so that we are always targeting exactly the same location, weather permitting and water level permitting, to run the jet erosion test. This is a summary of the soil physical characterization. And while in the other study, this was actually something that changed across all of the sites that we collected, in this study, this is something fixed. So we're actually looking exactly at the same soil every time that we go. The only thing that is changing is how wet the soil is, how hot the soil is, and then the electrical conductivity, which, as I said, is just a combination of the two. So you can see that the soil, if we only look at the median grain size, you will see that the soil is all relatively similar. But then if you look into much detail about what is the percentage of fine sand and gravel, you will see that you have soils that are primarily sand, but then the percentage of fines actually change. And not only the percentage of fine, but what is composing that percentage of fine. So everything that is less than 75 micrometers is basically clay and silt. And as you can see in the ASTM classification, we have soils that are mostly clay. There were a combination of clay and silt, or soils that are mostly silt, the percentage of fines. So we are actually capturing both soils that are on the two extremes that we tested in the previous case. So we have a soil that is more than 50% fines and one that is less than 10%. And then most of our soils are those in the middle that we didn't actually know what was happening because of the limited amount of data that we had. This, what I'm showing you right now, is actually the moisture content and the temperature across all of the different times that Carol and Sam went to take or to run a jet erosion test. So you see at the bottom of the screen the number of jet testing that has been performed as of last week. So about 9 to 10 in each one of the sites. And then every time they go there, again, they target the same site, and then they measure with the soil probe moisture content, temperature, and electrical conductivity. And what you can see is that even though you are in the same stream, you will have a variability of what is the moisture content and the temperature depending on where you're testing, of course. For example, if we focus on Walnut Creek sites, Walnut Creek site 1, locations A, B, and C, you have location A, which is actually the one located towards the upper part of the bank. And you can see that the percentage or the variability of moisture content is actually it's about 30, the mean, and then you have some variability. You can see that the variability is much less in the toe because it tends to be submerged for longer periods of time. And then you see that it's more than 40% in moisture content, and then it's not as variable. And then you have, for instance, the location C that tends to be exposed during low flow conditions and only gets saturated during high flow conditions. And you see that, and the material here is significantly different. So it's able to drain or to absorb water much differently than the other two. But this is exactly what we were aiming for. We were aiming for sites where we can actually see this variability, and not sites where we were going to go and then the moisture content, the temperature, and the electrical conductivity was going to be practically fixed as we measure. So that will not allow us to capture this temporal variability. All right. So this is a busy slide, but I selected because I think it really paints a much clearer picture of what we were trying to unravel in the regional study. So I have selected Walnut Creek site 1. So this we're looking at, if we move from left to right, we're looking at the relationship between the erodibility coefficient and the critical shear stress in the two axes. And then the color bar basically indicates the percentage of moisture content. So we're looking at the relationship between these two for the upper right bank. So this will be location A. For the toe of that same bank, this will be location B. And then for the toe of the opposite bank, the left bank, which will be location C. What you have in red is the percentage of fines divided between clay and percentage of silt. So you can see that if we start from location A, you have a percentage of clay that is 8.9 versus 14.3 of silt. And then that percentage of clay increases for the toe, which makes sense because you are going to have basically a depositional layer of fine material. And then you have location C, which actually has a very low percentage of clay, a very low percentage of silt. And as you see on the table at the bottom, it has actually a high percentage of gravel. So this is a toe that is actually characterized by a lot of bed material deposition. And it's a bit different to what you will expect in a normal bank, as you see in location B. So what I'm showing here at the top is basically the Pearson correlations coefficients that basically will tell you how the critical shear stress and the erodibility coefficient are varying linearly with the moisture content. So basically a negative value will indicate a negative correlation, and then a positive value will indicate a positive correlation. So what you see is that we have similar type of behaviors to what we saw in the regional study if we focus on the location B and location C. So location B will be the location where we have a very high percentage of fines. So we have about 50.5% of fine material. So this is a high plasticity clay. And what you see is that the Pearson correlation coefficient is negative for tau sub C, and then it will be positive for K sub D. So you have a critical shear stress that decreases with increasing moisture content, and then you have an erodibility coefficient that actually increases with increasing moisture content. And you can see that in the relationship right here. So you see that the critical shear stress is going down as the color changes from blue to yellow. And you can see that K sub D is actually going up as the color changes from blue to yellow again. So that will be representatives of those only 3 points that we have for the regional study. And then if you move to location C, which again is the toe that is well-graded sand with gravel, what you can see is that you have a critical shear stress that is actually positively correlated with moisture content, as we saw for the regional study. So you have a critical shear stress that increases as the soil becomes more saturated. And you have the opposite behavior for K sub D. So you can see here that K sub D basically goes from a maximum value of around 400 cubic centimeters per Newton per second, all the way till close to zero when you have an increasing value in the moisture content. So these two will be representative of that. And what I want you to also understand about this graph is that here we're looking at exactly the same soil. And the changes in KD and tau C basically imply that the same soil can behave significantly different whether you have changes in moisture content, temperature, and electrical conductivity. So it's exactly the same soil that we're just characterizing the temporal variability. And then what you see in point A, which is the upper right bank in Walnut Creek, is that here we have a behavior that is actually in between the two. So we have critical shear stress that is actually negatively correlated with increasing moisture content. And we also have an erodibility coefficient that is increasing, negatively correlated with increasing moisture content. So as this particular soil becomes basically more saturated, then you have that this soil will become more erodible, right? Lower force, and then you have lower force to initiate motion, but then you have a decrease in the value of K sub D. So what we saw when we're trying to characterize the variability through the lens of the streams within the city of Raleigh is that if we're looking at the same location for changing hydroenvironmental conditions, then the content of fines, so basically what is the percentage of clay and silt in that particular material, actually modulates the initiation of motion. So the percentage of fines, I didn't show the specific results here, but the variance that we saw in all of across the whole data set for tau sub C was actually explained by the changes in the contents of fine. And the other thing that we noticed that we didn't have the ability to see in the regional study is that the percentage of clay seems to play a key role in determining the functional form of erosion behavior. So clay is very sensitive to changes in moisture content. It's very sensitive to water. So the amount of water and the amount of exposition that that particular bank has, depending on the amount of clay, that will set not only the critical force, but it will also set how fast that material is moving once the erosion starts. And this is a data set that it's brand new. So I think all of these plots were generated about 2 weeks ago, since we're continuously collecting data. And this is a study that will continue to happen until August of next year. So we expect to continue going to the field about every 10 days and really increase this. And really what we want to do with these two data sets as a group is to develop basically a predictive equation that allows to characterize or to predict tau sub C and K sub D from the changes that we're seeing across the North Carolina Piedmont region and also in the streams within the city of Raleigh. But the main conclusion, and I think the take-home message from this presentation, is that if we go back to our research question, so how do stream bank erodibility parameters vary in response to changing hydroenvironmental conditions, is that what we notice and what the data suggests is that the behavior of these parameters is dynamic. And this is really a change in mindset in terms of how we treat these erodibility parameters or bank erosion in general. So if you look for many of the models, if we're talking about process-based model, they frequently assume that these two parameters are driven by the soil, meaning that for me, it's enough to go characterize the material as, let's say, sand, and then with that characterization, go ahead and predict what will be my tau C and my K sub D, so what will be the force and the rate of detachment, and then that's something that I will consider to be fixed. And what we're showing is that that's only part of the story. Soil properties are important, but then the hydroenvironmental conditions are actually affecting how these parameters change temporally. So soil properties will make them change, especially hydroenvironmental conditions will make them change temporally. And the important part about this is that this will really make these erodibility parameters change across the whole face of the bank. And we will talk about a little bit towards the end about how do we harness all of this variability and this understanding to actually make more accurate predictions. And if you consider these two pictures that I have on the bottom, and these are from two different sites. So this is the picture that I like to use in many of my presentations for stream bank stratification from Kernersville. And then the right is just 1 year of record of water height at the Walnut Creek gauge that is located downstream of our site. And what you will see here is how flashy it is. So the idea of putting these two things together is that think about how all of this variability, not only in the peak and the intensity, the peak or the duration of this event, but also how frequent they happen, will actually change the erodibility parameters as you see this flow record basically superposed into this material. So if this bank experiences many events that are continuous, let's say you have several 2-year flood events that are happening, that will change the erodibility behavior dynamically of this bank. Whether if you have a long dry period and then you have a major event, we're talking maybe about a 10-year event that will cause a certain amount of erosion. So the message is that it's not really about the magnitude. It's not really about understanding this event will generate more erosion, but it also has to do with what is the sequence of flows that are actually affecting how dynamic these parameters are. So how can we harness this understanding to improve predictability of stream bank erosion? And this is something that we're working right now. So this is phase 2 of the WRI project, and we are starting to look into this more closely. So the outcome, before I talk about what you're seeing on the screen, is that we want to move from approaches that basically have one erosion rate predicted from one force to approaches that basically talk about what is the rate of occurrence of a particular stream bank erosion rate. So rather than a discharge setting, this much erosion in a stream, then what are all of the possibilities of discharges and moisture contents and electrical conductivities and materials in this stream that will then generate a rate of occurrence. And with this rate of occurrence, then we can take a much more informed decision about, what is a level that is actually acceptable for a particular application, either stream restoration, either bridge scour or infrastructure protection, and then use that rate of occurrence as a way of understanding how all of the possible outcomes and the variability that may happen, that may have happened not only in the past, but also in the future that we don't understand yet, may actually affect the range of erosions that I can see in this stream. If you look specifically at what I'm showing, this is actually a framework that was developed by Bowers et al. To understand the rate of occurrence of atmospheric rivers. Atmospheric rivers, all of these researchers are from the West Coast, and it's a problem as actually there is one happening as we speak that generates a significant amount of flooding, and they generate obviously a significant amount of loss estimate because of flooding. So what we like about this performance-based approach and basically the advantage that it provides is that it is modular in the sense that if you see for this particular application, what you see in each one of these boxes is actually a different model that they use to basically go from the occurrence of precipitation to hydrologic and routing to inundation level. So if you think about what we're doing right now for stream bank erosion, we're going to basically transform or adapt this framework into if we have a particular distribution of moisture content, a particular distribution of electrical conductivity and temperature with a particular set of different materials, then we're going to apply these performance-based probabilistic approaches to finally generate a stream bank erosion curve that is based on rate of occurrence versus stream bank erosion, and then be able to inform whatever application it's of interest using this type of mental framework, if you wish. So that's all I have. If you have any questions, I'll happy to take them, and I hope to be, to update you soon in how those curves look like actually. And one thing that we're working on is actually making that something applicable. So we're considering not only developing all of that for our own research, but also try to make this publicly available so that we can have, for example, a Jupyter notebook with a graphical user interface that then somebody can access. They can input all of the information that is required to apply the framework, and then we can have at least estimates with confidence intervals of what will be that rate of occurrence for a particular erosion rate given those conditions. Thank you.
All right, thank you so much. Got a question. What part does severe drought play in stream erodibility prediction?
Yes, I think it will play, at least in the context of this presentation, it will play a role into making that material very dry. Basically, if you look, for example, if we go back to this particular screen for Walnut Creek, it will obviously change the moisture content, for example, and then it will change the relationship between the critical force and the detachment rate. So depending on the composition, if you're talking more about a sand material or a clayly soil or something more high plasticity, then it will definitely change the behavior if you're experiencing a big storm after a very long drought period, or if you're experiencing that very same storm after a lot of rainfall events. And I think that's something that we realized when we were doing these measurements, that we tend to think about larger storms, larger erosion rates. But in reality, it can be more of a cumulative effect. You can have relatively small storms that happen more frequently, generating a much larger amount of geomorphic change in the streams that what you can have with one single event, depending on the magnitude of that event.
All right, thank you.
Thank you.
Without any other questions, I think now we will close out the conference. Definitely want to thank all of our speakers and everyone attending the conference, the Water Resources Committee and Stormwater Partnership for making this possible. Thanks so much for being here, and have a great day.
Thank you, Dr. Bolinaga.